The launch of NASA's Voyager probes marked the beginning of a historic interstellar journey, demonstrating our ability to monitor not just Earth but also our solar system and beyond. Even after 45 years, these remarkable spacecraft continue to provide scientists with updated insights about space. Despite having a memory capacity 3 million times smaller than a regular smartphone and 38,000 times slower than a 5G internet connection, these incredible probes remain at the forefront of space exploration. But now, in a shocking twist, the Voyagers have stumbled upon an impossible discovery. What are they doing right now? What will the Voyager spacecraft encounter? Let's find out. On September 5, 1977, from Cape Canaveral, Florida, a remarkable journey commenced as Voyager 1 was launched into space, propelled by the Titan IIIE/Centaur rocket. Only 15 days later, on August 20, 1977, Voyager 2 followed suit, embarking on a twin odyssey into the cosmos. Their primary mission was to explore the gas giants of our solar system, Jupiter and Saturn, and the moons that orbit them. However, these brave explorers far exceeded their initial objectives, embarking on a journey that would take them to the farthest reaches of our celestial neighborhood. Voyager 1 and Voyager 2 have set numerous records during their epic voyage. They have lasted longer than any other spacecraft in history, and their travels have taken them further from Earth than any other human-made objects. In fact, they have entered interstellar space, making them the first human-created objects to do so. Their journey into interstellar space, beyond the Sun's sphere of influence and into the uncharted territory of the galaxy, has provided scientists with invaluable data. As pioneering interstellar probes, more than 12 billion miles from Earth, they continue to surprise physicists with their findings. The recent impossible discovery is one of those finds scientists could never predict. We will examine it in greater detail later. The achievements of the Voyager twin probes have been nothing less than spectacular. Their early observations of Jupiter and Saturn's moons made more than 40 years ago astonished researchers and defied previous assumptions about these distant worlds. These moons, which astronomers once believed would be as inactive and heavily cratered as our own moon, turned out to be packed with geological activity. Voyager 2, in particular, achieved several significant milestones during its journey. It became the first spacecraft to pass by Uranus in 1986, and just 3 years later, it conducted a flyby of Neptune. To this day, it remains the only spacecraft to have ventured on such a path. As the spacecraft continue their remarkable voyage, NASA has implemented a series of measures to extend their operational lifespans. Over the past 3 years, non-essential components and heaters have been turned off to conserve energy, allowing them to operate well into the next decade, with an estimated mission end date of 2030. For the scientists and engineers who have been part of this extraordinary journey from its inception, the culmination of the Voyager missions is a bittersweet moment. Their dedication and hard work have seen the project through far beyond their initial expectations. The data returned by the Voyagers has provided valuable insights, fueled countless scientific discoveries, and inspired generations of researchers and space enthusiasts. Voyager 1 and Voyager 2 were not just ordinary spacecraft. They were meticulously designed to be stable platforms, with a rotation rate more than 15 times slower than the hour hand of a clock. This design minimized any visual blur as the spacecraft captured images and data while hurtling through space. Their impressive imaging capabilities began to astound scientists and the public even before their encounters with the outer planets. The spacecraft started transmitting images of Jupiter while still several months away from the planet. These early images, revealing the gas giant's swirling clouds and iconic Great Red Spot, delighted audiences at NASA's Jet Propulsion Laboratory. However, it was the discovery of active volcanoes on Jupiter's moon, Io, that truly set the stage for the Voyager's groundbreaking observations. Io, slightly larger than Earth's moon, turned out to be the most volcanically active body in the solar system. The spacecraft's instruments detected peculiar signals from Io, which were confirmed by the vivid images they captured. These images revealed towering volcanic plumes and a surface marked by the ejection of volcanic material. Pele, one of Io's most prominent volcanoes, has erupted 30 times higher than Mount Everest, covering an area nearly the size of France. The Voyager spacecraft captured over 33,000 images of Jupiter and its moons, showcasing the planet's beauty and the incredible diversity of moonscapes in the Jovian system. Before the recent impossible discovery, the twin Voyagers have been making spectacular discoveries since their launch. One of the most surprising findings was the existence of Jupiter's rings. These rings, though faint, were a revelation and added to the intrigue of the gas giant. Additionally, Voyager 2 revealed that Europa, one of Jupiter's 53 named moons, possessed an icy shell believed to be over 60 miles thick. These findings challenged previous assumptions about the nature of these distant celestial bodies and inspired further investigations into the potential habitability of icy moons. As the Voyagers departed from Jupiter, they received a gravity assist that provided them with a farewell kick, propelling them toward Saturn. Without this vital boost, they would have been unable to escape the Sun's gravitational pull and venture further into space. Voyager 1 and Voyager 2 soon went their separate ways, each heading towards new frontiers. Voyager 1's path took it close to Saturn's moon Titan, which is cloaked in an orange, hazy atmosphere. This moon's mysteries piqued scientists' interest, leading to further studies of its complex chemistry. Voyager 1 then turned northward, departing from the plane of the planets, and began its journey beyond the realm of our solar system. Voyager 2, on the other hand, embarked on a series of adventures that brought it to the outermost planets of the solar system. In 1986, it made a historic flyby of Uranus, where it discovered 10 previously unknown moons, increasing the planet's moon count. 3 years later, Voyager 2 reached Neptune, revealing the remarkable features of this distant ice giant. During its encounter with Neptune, Voyager 2 recorded wind speeds of up to 1,000 miles per hour, making it the fastest wind ever recorded on a planet in our solar system. As the spacecraft passed within 2,980 miles of Neptune's azure methane-rich atmosphere, it provided unprecedented insights into this distant world. Triton, Neptune's largest moon, was found to be one of the coldest places in the solar system, with surface temperatures plummeting to -391 degrees Fahrenheit, -235 degrees Celsius. Triton also exhibited unique features, including ice volcanoes that ejected nitrogen gas and icy particles 5 miles into its thin atmosphere. These discoveries expanded our understanding of the variety and complexity of celestial bodies in our solar system, even in the outermost regions. One individual who played a pivotal role in extending the missions beyond their initial goals was the renowned astronomer Carl Sagan. As a member of the Voyager mission's imaging team, he passionately advocated for capturing one last set of images before the cameras on both spacecraft were turned off. These images would offer a parting gift to humanity, a final glimpse of our home planet from the distant depths of space. Sagan's persistence paid off. On Valentine's Day in 1990, Voyager 1 turned its camera back toward the inner solar system and captured a series of 60 images. The most iconic among them, known as the pale blue dot, remains an unforgettable symbol of our place in the cosmos. Taken from a distance of 3.8 billion miles, it is the farthest image of our planet ever recorded. Earth appears as a tiny, pale blue speck, barely distinguishable in the vastness of space. The Voyager mission is an astonishing tale of durability and longevity that reads like a space-age superhero comic. And even after 40 years, they're still out there, continuing to send us valuable data from the furthest reaches of our cosmic neighborhood. Now, let's talk about their archaic 8-track tape system. Yes, you heard that right, 8-track tapes were all the rage in the 70s, and the Voyager probes still use them. It's a testament to the genius of the mission's designers that these trusty tapes have stood the test of time. But why 8-track tapes, you ask? In those early days of space exploration, digital storage as we know it today was still in its infancy. So, they needed a reliable and durable data storage system, and those 8-track tapes fit the bill. They're like the indestructible workhorses of the cosmic age. What's even more incredible is that the data on these tapes isn't just your run-of-the-mill tunes, its precious scientific data about the outer planets, moons, and interstellar space. That's right, these tapes hold the key to understanding some of the most profound mysteries of the universe. As for durability, think about this: the Voyager spacecraft are exposed to extreme temperatures, cosmic radiation, and the vacuum of space. And yet, these aging explorers keep on going. It's like sending your grandparents on a trek through Antarctica, and they not only survive but thrive. One important technique used in the Voyager missions was gravity assist maneuvers, and their role in these legendary interstellar missions was nothing short of brilliant. Imagine two brave spacecraft, Voyager 1 and Voyager 2, setting out on their audacious quest to explore the outer reaches of our solar system. To reach these distant destinations and gather invaluable data, they needed a boost, something more than their own propulsion systems could provide. This is where gravity assists come into play, and it's a bit like cosmic choreography. Instead of relying solely on their engines, these spacecraft performed a celestial dance with some of our solar system's heavyweight planets, using the immense gravitational pull of these giants to slingshot themselves on their way. This clever maneuver allowed them to conserve precious fuel and gain the velocity they needed to visit multiple destinations on their grand tour. Let's start with the basics. Gravity assist, also known as a gravitational slingshot, is all about transferring some of a planet's momentum to the spacecraft as it passes by. Picture Voyager 1 approaching Jupiter, a massive gas giant with a gravitational pull to match. With precision that could only be achieved by the brightest minds at NASA's Jet Propulsion Laboratory, Voyager 1 swung by Jupiter at just the right angle and speed. Jupiter's gravity tugged at the spacecraft, accelerating it to a higher velocity. It's like a cosmic boost, giving Voyager 1 the oomph it needed. But there's an art to this maneuver. If Voyager 1 had approached Jupiter at the wrong angle or speed, the slingshot could have been a cosmic catastrophe, sending the spacecraft off course. The precision required is mind-boggling. Yet, the scientists and engineers behind this cosmic ballet got it right, not just once but multiple times. These gravity assists propelled Voyager 1 and Voyager 2 on a breathtaking journey through the solar system. Voyager 2, for instance, used gravity assists from Jupiter and Saturn to take it to Uranus and Neptune. These celestial dances were pivotal in making the grand tour possible. The Voyager missions would not have been the same without these slingshots. Voyager 1 went on to reach interstellar space, and Voyager 2 quickly followed suit, all thanks to the precision of these gravity assists. The concept behind gravity assists is simple, but the execution is breathtakingly complex. Voyager 2's grand tour required so much precision. Missing any of these slingshots could have meant a failed mission. But the people behind these missions were determined and relentless in their pursuit of knowledge. Although the Voyager missions made use of gravity assist maneuvers to navigate the cosmos, these missions would have been mere celestial daydreams without another critical component, the Deep Space Network, DSN. Think of it as the interstellar telephone line that kept us connected with our intrepid Voyager probes as they journeyed into the great unknown. So, what exactly is the Deep Space Network? It's not as flashy as a spacecraft, but it's just as vital. The DSN is a network of massive radio antennas strategically located in various corners of the world, including California, Spain, and Australia. These gargantuan dishes, ranging from 26 meters to a whopping 70 meters in diameter, are like cosmic megaphones, allowing us to communicate with spacecraft traveling beyond our planet. Now, let's talk about its role in the Voyager missions. The Voyager probes, with their cameras, sensors, and instruments, were essentially our eyes and ears in the vastness of space. To make sense of the data they sent back and to give them new instructions, we needed a robust communication system, and that's where the DSN stepped in. Picture this: Voyager 1, on its way to the outer reaches of the solar system, sends a message back to Earth. It's a faint signal, traveling at the speed of light. As it traverses the cosmic expanse, it weakens. By the time it reaches Earth, it's barely a whisper. But the DSN's colossal antennas are poised to catch that whisper. They lock onto Voyager's feeble signal and amplify it, turning it into data that scientists can analyze. The DSN doesn't just receive signals, it also sends commands. You see, missions like Voyager are dynamic. Scientists and engineers need to tweak their plans, redirect the spacecraft, or adjust their instruments. They send these commands via the DSN, which beams them into space to reach Voyager. It's a two-way conversation between Earth and the farthest human-made objects in the cosmos. One of the remarkable things about the DSN is that it operates 24/7, tirelessly listening for those distant signals. It's like having an unblinking eye on the cosmos, keeping us connected with our spacecraft, even when they're billions of miles away. The Voyager missions are a testament to the power of collaboration and innovation. While the spacecraft embarked on their incredible journeys, the DSN made sure they were never truly alone. It bridged the gap between our planet and the unknown, allowing us to explore the outer planets and venture into interstellar space. In essence, the Deep Space Network isn't just a collection of antennas, it's our lifeline to the cosmos. It ensures that the stories of the Voyager missions continue to be written, even as the spacecraft journeys beyond our solar system, into the uncharted territory of interstellar space. As the Voyager probes were on their interstellar journey, one of the key milestones they had to navigate was the heliopause. It's the boundary that separates our sun's influence from the vast interstellar space beyond. The exact location of this boundary was a bit of a mystery, with various estimates and theories. Early estimations placed it as close as Jupiter, but subsequent calculations refined our understanding. In 1993, projections by astronomer Bill Gurney placed the heliopause between 116 and 177 astronomical units, AU. To put this into perspective, 1 AU is roughly 93 million miles. The distance between the Earth and the Sun. Gurney's projections turned out to be remarkably accurate, as Voyager 1 reached the heliopause about 20 years later and detected the expected rise in plasma density. However, it posed a puzzling question. When Voyager 1 reached the heliopause, it observed an increase in plasma density but no significant shift in the ambient magnetic field direction. This was unexpected because if the spacecraft had traveled from a region where the magnetic field originated from the Sun to one where it came from other stars, noticeable change should have occurred. Voyager 2 added to the mystery when it reached the heliopause at the same distance as its twin, $120 from Earth, but also failed to detect any magnetic field changes. Theoretical models predicting the behavior of the heliosphere and its interaction with the interstellar environment faced challenges due to these unexpected observations. The heliosphere was expected to fluctuate in sync with the Sun's 11-year cycle, but this did not align with the data gathered by the Voyagers. The solar wind, which ebbs and flows with the Sun's cycle, was at its strongest when Voyager 2 arrived at the heliopause. The predicted position of the heliopause should have been further out than $120, adding another layer of complexity. Nevertheless, the Voyager's data have provided valuable insights for refining theoretical models. Scientists now believe that our Sun has transitioned from a hot, ionized zone to a partially ionized section of our galaxy. This transition was likely triggered by nearby supernovae, ancient stars that exploded at the end of their lives and heated the surrounding area while removing electrons from adjacent atoms. The boundary between these regions can be likened to a seaside, with turbulent waves and mixed magnetic fields. Although the degree of turbulence can vary, the Voyager's observations have revealed small-scale changes near the heliopause but negligible variations on larger scales. The ageless explorers, Voyager 1 and Voyager 2, continue their solitary journeys through interstellar space, leaving behind the planets and moons they once called home. But what lies ahead for these indefatigable travelers? It's a cosmic guessing game, but here are some possibilities to ponder. These probes are now headed in different directions, with Voyager 1 racing toward the constellation Ophiuchus, while Voyager 2 is making its way toward the constellation Cetus. Although it may sound like they're headed for a cosmic death in 2030 as predicted by some scientists, it is still possible that they'll likely outlast our species, enduring for millions of years. One day, they might encounter other star systems, bringing with them a message from a long-lost Earth. Picture an alien civilization stumbling upon these ancient artifacts of human ingenuity, carrying the golden record, a time capsule of our existence. Who knows what mysteries they might uncover?